Hi everyone, today we're looking at the very first day in our next unit. This is unit number 5. This is all about quadrilaterals. Except on day 1, we're not just focusing only on quadrilaterals, we're looking at all kinds of polygons. So there's a lot of vocab words to get through here on the first page. So day 1 and day 2, we'll really look at interior angles and exterior angles of polygons. And then once we get to day 3, then we'll get to all of the special properties of various quadrilaterals. So that's where we're headed. So you know that we have a triangle and a quadrilateral with 3 and 4 sides, but here are some other names. See if any of them look familiar. 5 sides is a pentagon, 6 is a hexagon, and 7 is a heptagon. 8 is an octagon, nonagon, decagon, dodecagon, and if there's any other number, we just put the number right here with a little hyphen with that G-O-N. So if there's 20 sides, we would just write down 20-gon. And that way it covers all other kinds of shapes. Here are some other vocab words that we've seen before, like interior and exterior angles. So take a look at this part right here. Here's a little sketch. Here's a triangle. Here's a, let's call it a trapezoid. If you extend one side, then you can see that the interior are inside and the exterior is, well, it's a linear pair with the interior, right? They will add up to 180 degrees. So that's what we mean with those interior and exterior angles. We've seen these words before as well. If a polygon has all of its interior angles congruent, we call it equiangular. If all of its sides are congruent, we call it equilateral. And if it's both equilateral and equiangular, then we call it regular. And so that's a key word that we'll be seeing quite a bit today and tomorrow. Tomorrow especially, I think. Here, if we have vertices, we want to identify which ones are the ones that we call consecutive vertices. In a polygon, 2 vertices that are the endpoints of the same side are called consecutive vertices. So here, for example, I have 5 sides. We have 5 vertices, and if you're looking at one particular side, any vertices that are touching that same side, those are consecutive. So we don't call them adjacent. In geometry, we define adjacent as being, for example, 2 adjacent angles. They have to share a common side and a common vertex. Here, these 2 angles share a common side, but they don't share a common vertex. So they're not adjacent. We call them consecutive. Here, with some of the notation of different shapes, we've studied triangles in the past, so we're quite familiar with putting that little triangle symbol in front of the 3 letters naming the vertices to name the triangle as a whole. If it's a parallelogram, we put this little tiny miniature parallelogram in front of the letters, and we read it out loud by saying, parallelogram A, B, C, D. That's what you have right there underneath the line, how you read it. But if it's not a parallelogram, if it's any other kind of quadrilateral, there is no special symbol. We just write down the letters of the vertices. And when we read it out loud, we say figure, E, F, G, H. And if you have any other polygon, like this one below, here we have 5. Notice that we just pick a vertex to start at, and it doesn't really matter where you start, but we go clockwise around or counterclockwise around. So we could call this figure C, D, E, A, B, or we could call it figure C, B, A, E, D. If we started at C, we could start anywhere we wanted to. And lastly, we're looking at what we mean by diagonals versus sides. A diagonal of a polygon is a segment that joins 2 non-consecutive vertices. Okay, so here is a side. It is joining 2 consecutive vertices. But if I go through the figure to a non-consecutive vertice, that's a diagonal. So the diagonals are on the inside, the sides are on the outside, the perimeter of the figure. We're going to be taking a look at how to add up all the angle measures of these polygons. And to help us do that, we're going to look at this table below and look for patterns in the numbers to see if we can find out how many degrees do those angles add up to. Starting off with this simplest shape of a triangle, we've used this before. We know that a triangle's three angles add up to 180 degrees. That's something we've memorized already. The trick is, can we take some of these other shapes and represent them in terms of triangles? So I'm going to pick one vertex, this one for example, and I'm going to draw a diagonal so that now we have triangles side by side. We don't want overlapping triangles. So if this triangle's angles add up to 180 degrees and this triangle's angles add up to 180 degrees, then the quadrilateral as a whole is really two triangles combined. That means we have two triangles. And two triangles at 180 degrees apiece means that there are 360 degrees total inside a quadrilateral. For my pentagon, if I pick a vertex and draw diagonals from it, we have now two diagonals, and that means we have a total of three triangles. So that means if we have three triangles at 180 degrees apiece, well, then that means the total number of degrees in that pentagon is 540. We can see the total sum is increasing with the more sides we have. Here's our hexagon with 6 sides. I'll pick a vertex, draw some diagonals, and we get a total of 1, 2, 3, 4 triangles on the inside. So 4 triangles times 180 degrees apiece means the total is 720. Now there's a pattern here in the numbers, and what we're trying to do is we're trying to get to this point here. How do we calculate the total amount of degrees for any polygon? We're using n to represent the number of sides. Could be 10 sides, could be 20 sides, whatever. We want to be able to figure out how many degrees that polygon will have. So in looking at this table, notice we always found the number of triangles and multiplied it by 180. So the question is, how many triangles will there be in a polygon with n sides? Well, notice the pattern. 3 sides had just 1 triangle. 4 sides had 2 triangles. 5 sides had 3 triangles. 6 sides had 4 triangles. The number of triangles was always smaller than the number of sides. How much smaller? Exactly 2 less. So if I have n sides, how many triangles would I find? 2 less than that. So we would represent that with n minus 2. That's how many triangles there will be inside a polygon with n sides. So we're going to take the number of sides, the n minus 2, multiply it by 180, and now we have a little process, a little equation to help us calculate the total number of degrees inside any polygon we want. That's the explanation for where this comes from. Now let's go and take a look at some examples. So heading over to the next page. To summarize at the very top, there you see the box. The sum of the measures of the interior angles is n minus 2 times 180. Put a little equal sign there. And that's in degrees. Okay. That has an official name. It's called the Polygon Interior Angles Theorem. It is a theorem, which means it can be proven. We're not going to actually prove it this time, but it can be proven. And based on that, we have a corollary. Remember, a corollary is a special case of that theorem. We are looking at a quadrilateral. We've already seen that a quadrilateral's angles add up to 360, and that's so useful, you might just want to memorize that one. So let's find the total sum. Let's find the sum of the angle measures of these polygons. So here in part A, we have a heptagon. How many sides is that? All right, that's 7. We saw that vocab list on the previous page. So the interior angle sum is equal to that n minus 2 times 180. What I'm doing is I'm taking that information from the box above and just kind of summarizing it slightly, condensing that down for this left-hand side. That's the formula that we're using in this section. So my interior angle sum will be found by, substitute that 7 in place of n. And this is all calculator work. You just type that in. You're using our order of operations. So 7 minus 2 is 5, 5 times 180, and the calculator tells us the result. 900 is the total degrees. Let's take a look at another one. for a nonagon. Do you remember how many sides that is? 9. So the interior angle sum is, there's the formula, let's drop the 9 in for the n, 9 minus 2, that result times 180. So you can just type that in your calculator, you should get 1260. Don't forget the degrees. Here's one more. What if it's a 22-sided polygon, a 22gon? All right, we can do that. The interior angle sum is 22 minus 2 times 180. Again, with these big numbers, we're relying a lot on our calculator to get this done. So 3,600 degrees. Now we're using the same formula in the next row of examples, but there's a little bit of a twist. Now we're going to go backwards. Example 2 says, the sum of the measures, right, that's the left part of the equation. The sum of the measures of the interior angles is given. So they're actually giving me the total. We have to work backwards to find the number of sides. And when they say classify, that means give it the name. So not just the number of sides, but what is the name of the object with the number of sides you just found. All right? So here in part A, we have a polygon whose interior angle sum is the 1,080 degrees. So that goes here on the left side. And that equals the n minus 2 times 180. So we're solving this equation backwards to figure out what is n. How many sides is that? So, because of the parentheses, we have to first get rid of that 180. Let's divide both sides by 180 degrees. So on the right-hand side, you now have the n minus 2 by itself. On the left, again, use your calculator here. That turns out to be exactly 6. And lastly, isolate your variable by adding 2 to both sides. So we have 8 sides in this polygon. But the question is, can you give it the name? That's the classification. Yes, it's an octagon. And there's your answer. All right, let's try another one. What if it has 1440 sides? Excuse me, that's not sides. That's the total angle sum. 1440 degrees, again, goes here on the left-hand side. So 1440 equals the n minus 2 times 180. To solve for n, we start by dividing both sides by the 180. The calculator tells me that results in 8. And lastly, to isolate the variable, add 2 to both sides. All right, so it has 10 sides. But can you classify it? That's a decagon. And here's one more. Here's part C. 3420, that's supposed to be in degrees. That's a typo there. That's supposed to be an angle sum, so of course you have to have a degree symbol. So 3420 equals the n minus 2 times 180. Like before, let's solve for n. We start by dividing both sides by 180. All right, my calculator tells me that gives me a result of 19. That equals n minus 2. So to isolate the variable, let's add 2 to both sides. And we get 21. Okay, it has 21 sides. What's its name? How do you classify it? Well, we don't have a special name for it. We just call it a 21gon. It's a 21-sided polygon. That's its name. So we want to finish up with examples 3 and 4. They're kind of similar. Here we have 4 sides. Here we have 5. And in each case, you can see that we want to find the unknown angle measure. And there are some missing angles. So if you happen to remember that a quadrilateral has its angles add up to 360, right? We saw that here. Well, then we're going to add up these angles to 360 degrees. All right, so x plus 71 plus the 112 plus the 135, they add up to 360. But what if you didn't remember that they add up to 360? Then we might be in trouble, right? No, not necessarily. As a first step, we could calculate that. This is just if you're drawing a blank. We recognize, hey, this has 4 sides, right? And then we use this formula that you've been seeing above. The interior angle sum is equal to n minus 2 times 180. So if you drop a 4 in for n, 4 minus 2 times 180, you get 360 degrees. So even if you were to forget how many degrees there is, we can always calculate it as a first step. Then, as a second step, we could set up the equation, adding up all 4 angles to 360. Let's combine our like terms. Again, my calculator is helping me out here. Adding up 71 and 112 and 135 gives me 318. So x plus 318 equals 360. Let's move all the constant terms to the right-hand side, subtracting 318 from both sides. This isolates the variable. We get a result of 42. So that's the concept. We want to do this again now with a figure that has yet more sides. So what's the total number of degrees with 5 sides? Oh no, I don't remember. I better calculate that. So here's my first step. My interior angle sum equals n minus 2 times 180. We have 5 sides, so 5 minus 2 times 180 means that I'm working with a total of 540 degrees. Now, for my second step. Now we're going to add up all the angles to that many degrees. So we have a 68, we have a 105, we have a 109, we have a, that's odd. I don't have anything here, and I don't even have a variable. Well, I guess we should pick one. In fact, notice that both angle L and K have this arc symbol. That means these two angles are the same size. So whatever variable we pick, they should both have the same variable. So I'm just selecting y. Y plus y. So we should have 1, 2, 3, 4, 5 angles. 1, 2, 3, 4, 5. So I just counted to make sure I didn't leave any out. And the 540 that we had from the previous step, there it is. That's what we add up our 5 angles to. Let's combine like terms. So 68 plus 105 plus 109 gives me 282. Y plus y is 2y. Let's move the constant terms to the right, subtracting 282 from both sides. So 2y equals 258, and then dividing away the 2, I have 129. Again, I'm just using my calculator with those big numbers. Now, the specific question is not find the variable, but to find the measure of the angle. So just to format that, we would say the measure of angle K equals 129 degrees. So notice the variable does not have the degree symbol, but the angle does have the degree symbol. Similarly, the measure of angle L, also 129 degrees.